Hi, my name is Mackenzie Smith, and this is my alum crystal lab 2 report. First, I'm going to talk about the progress of my crystals. A small collection of crystals have started to develop at the bottom of the vial. They look well formed and clear, and the solution has also developed a cloudy quality to it that I think is an indication of other crystals forming. After this slide, I've also included a video of a 360 view of my vial. I'm not sure if the development of my crystals is less than expected, but if it is, then there are some factors that could be hindering its growth. For example, in order for the solution to evaporate, it should be placed in an environment that will encourage evaporation. If the temperature around the vial is too cold, then it will make it harder for the solution to evaporate, and although the Kim wipe is in place to slow the evaporation process, it is possible that it has slowed it down too much. Here are the chemical equations necessary to determine the theoretical yield of alum. At the bottom of the slide, I've also included information regarding the molar mass of the chemicals that are relevant to the calculations. In order to determine the theoretical yield of alum, I've broken it down into roughly 6 steps. The first 3 steps are listed here, followed by example calculations of each step. The first step is to look at the first chemical equation and use massive aluminum foil to determine moles of AlOH4- produced. The second step is to look at the second chemical equation and use moles of AlOH4- to determine moles of aluminum hydroxide produced. The third step is to look at the third chemical equation and use moles of aluminum hydroxide to determine moles of Al2SO4 produced. The following are example calculations of the first 3 steps. Here are the last 3 steps of the process, which are also followed by example calculations. The fourth step is to look at the fourth chemical equation and determine the molar ratio between Al2SO4 and Al3+. The fifth step is to use this molar ratio and determine how many moles of Al3+ are present, and then find out how many moles of alum would be produced. The final step is to use the molar mass of alum to determine the theoretical yield of alum in grams. Using these steps, I got the theoretical yield to be 18.432 grams. Here are the example calculations for the 4th through 6th step. Using the theoretical and actual yield values, we are able to determine the experimental percent yield with the following equation. After doing the calculations, the percent yield comes out to be 79.586%. Our percent yield was not 100%, therefore there must have been a source of error during the experiment that affected the amount of product produced. One source of error could have been the inability to remove some of the product from the filter paper. However, the remaining product on the paper would not have accounted for the complete difference in theoretical versus experimental yield. Therefore, there are other sources of error that could have contributed to the difference in product. Another source could have been the amount of time it took for our precipitated aluminum hydroxide to dissolve back into the solution. Unfortunately, we started the cooling process before the aluminum hydroxide was fully dissolved, and this could have reduced the amount of final product we collected. Another source of error could have come from the final step of the lab, when the alum was supposed to fall out of the solution. We may not have allowed the precipitate to completely form, therefore reducing the final amount of product we collected.